to continue the previous talk. So just before my talk, and just tell you two things which I asked you to think about. I remember when I was at the end of high school, my teacher in a preparatory school made this gesture, and he told me, what is a parameter? And it took me some reflection to answer that the parameter is time. Okay. Now, so the link, the two remarks I want to make for the previous talk is that I have thought a lot for a long time about what are variables in mathematics and what are infinitesimals. And for Newton, the infinitesimals were infinitesimal variables as opposed to Leibniz. And the answer that you find for mathematics is that if you stay in the classical world, you cannot have a good setup for variables, because variables with continuous range cannot coexist with variables with discrete range. And when you think a lot more, you find out that there is an answer, perfect answer, and that this answer is coming from quantum mechanics, and that the true notion of variable, including in mathematics, should be an operator, self-adjoint for real variables, and that the real variability in the world is exactly that where are you in the spectrum of this variable, of this operator. And what is quite amazing is that, in this work which I did at the very beginning of my mathematical studies, the amazing fact was that exactly time is emerging from the non-commutativity. Namely, you think that the fact that these variables do not commute, first of all, it's because they do not commute that you can have the discrete which coexist with the continuum. Because you can have an operator which has discrete spectrum in Hilbert space and is the same Hilbert space as an operator with continuous spectrum, but of course they cannot commute. And what you find out after a while is that the origin of time is probably quantum mechanical, and it's coming from the fact that thanks to non-commutativity only can one write the time evolution of a system, which is a system in a heat bath in temperature, and the time evolution is really coming from the non-commutativity of the variables. So what I'm going to explain today is not at all unrelated to that, because somehow when you have this discourse from quantum mechanics and so on, you really are in a different world than the world of geometry, which we all like, because we all like to draw pictures, and we all like to think in a geometrical manner. And so what I'm going to explain is a way, if you want to address the problem of how to think about geometry. You will see it's a very strange way. It will look very strange. How to think about geometry from this point of view, which is quite different from the point of view of drawing on a blackboard, drawing some drawing and so on. And I will start by asking an extremely simple question, which is a question which has, of course, a geometric origin. And this question, I don't think there can be any simpler question. I'm asking, where are we? So there are several answers. You can tell me we are in Lille, in some center, so okay, on the planet Earth, and so on. Fine, but just try to communicate this to aliens. Okay, so imagine that you want to communicate to aliens where we are. Men have tried that. They have sent a probe. They've sent a probe, and when they have sent this probe, of course, they couldn't write on the probe we are in Lille, and so on and so forth. So they have tried to be as explicit as possible. And for instance, there is a clear meaning to the two guys on the right. Okay, there is also a very clear meaning for the bottom line, because in the bottom line you can see that there is a huge object, which is the Sun, then there is Mercury, then there is Venus, then there is the planet from which the probe has gone, because you can see that the probe, there is a trajectory of the probe coming from the third planet, and so on and so forth, and there is Jupiter, Saturn, and so on. All right, and then this, of course, is not satisfactory at all, because there is probably zillions of such things in the universe. And it's not telling in a univoc manner where we are, by any means. So, of course, physicists are very clever, and they made something which may look cryptic, but which is the most informative of all in this picture, and which is that they drew the various directions of 14 pulsars, and of the center of the galaxy starting from the Sun. And on each of them, they put the corresponding frequencies. Okay? And as we shall see, this is coming very, very close to the answer that I'm going to gradually obtain from mathematical pure thinking. And so the mathematical question which I am asking, in fact there are two questions. You see, well, what we want to say where we are, and this has two parts. We have to say what is our universe somehow, okay? So what is the geometric space in which we are, and in which point of this universe we are, okay? And so we cannot answer the second question before answering the first question, of course, okay? Now, if you think a little bit, you will find out that when you want to give an answer to the first question, I should have said that it doesn't help to be fancy to answer the question of where are we in the universe, because you could tell me, yes, I am a general relativist, I'm going to give you the coordinates where we are. Yes, but for which coordinate system, Where is the origin of the system and so on. So it doesn't help. So what you have to do, you have to be able to tell where we are, if you want, what is a geometric space where we are, in an invariant manner. Now, if you think about the invariance of a space that you can give, well, you will immediately find one invariant, for instance, which is, we assume the space is finite, let's say, at the diameter of the space, okay? That won't give you much. I mean, that will give you some information, but very little information. So since the usual model that we have for thinking about spaces is the Riemannian model, then you can ask, if I have a Riemannian space, what can I give as invariants of that space, which are naturally given? And what happens is that, of course, you can give invariants, and these invariants are, in a sense, refinements of the idea of the diameter. If you want, very roughly speaking, the inverse of the diameter of the space is related to the first eigenvalue of an operator. Okay, and this operator has many, many other eigenvalues, and this operator is actually encapsulating the vibrations of the space. So this lecture has to be taken into two different ways. There will be a way where you can hear the music of shapes, namely there will be a slew of invariants of a shape, of a geometric shape, which will be its scale in the musical sense. All right? So if you want, if I have a shape, this shape will have a certain number of notes. These notes will be given by their frequencies, and these frequencies will form the basic scale, okay, at which the geometric object is vibrating. Okay. On the other hand, one knows, don't be afraid by this page, this is the only technical page, essentially, in what I'm going to explain. So what one knows, however, for mathematicians, one knows that this sequence of frequencies, or if you want the scale of a geometric shape, is actually not enough to determine the shape. And we shall see examples very soon. Okay. However, what emerges, if you want, is that if you know not only the scale, namely the various frequencies which are possible, but if you also know the chords, and the point will actually be defined by the chords which correspond to this point. Okay, then you know the full thing. Then you are in complete knowledge of the thing. Okay, so this is what I want to explain, and I mean it's a rather delicate thing, but to explain it to mathematicians in 2 words, for mathematicians what happens is the following, is that there is a very strange mathematical fact, which is that if you take manifolds of the same dimension, which are extremely different, the way the algebra of measurable functions on this manifold is acting in the Hilbert space of spinors is the same. That's an old theorem of von Neumann. It doesn't distinguish between 2 manifolds. The Dirac operator itself has a scale, so it has a spectrum. And the only thing that you need to know in order to completely reconstruct the manifold with its Riemannian metric and everything is the relative position of the algebra of the basis of vectors, which are the eigenfunctions of the Dirac operator, and the basis which correspond to the measurable functions. When you know the angle, if you want, when you know the relative position of these 2 things, you know everything. Okay, so now let's do some very practical thing. So let's look at the music of very concrete shapes. Let's take, of course, I mean, this is, an old theme of Marquardt and all that. So I'm talking about a drum here, and I'm looking at the way it is vibrating. And, I mean, of course, it can vibrate in many, many different manners. And perhaps, if you want, there is something even simpler than this drum. Yeah, let me do that. Okay, which is what happens, in fact, with a single string. So if we take the most elementary shape, okay, which is the interval, what will happen is that when we make it vibrate, if you want, of course, we all the endpoints fixed. Then, I mean, it will vibrate in a very, very, very extremely simple manner, and each of these will actually produce a sound. Ooh, I hope. I mean, this has been a bit strange because I did it backwards and so on. All right. And, I mean, let me first tell you one thing. Naive people would think that if you take a string and look at these vibrations, you will be able to play music with that. That's actually not true. It's a very, very, very bad instrument. I will explain you why later. Okay. It's an extremely bad instrument. All right, so now let's look at the vibrations of the next one. So of course, when you look at the spectrum of this interval, well, you can see, I mean, the spectrum cannot be simpler. I can picture it as a spectrum here, and I can also plot it, and it looks like that. So it looks just very elementary as a straight line. So now if we take the disk, then, we can look at the various vibrations of the disk. There are 2 parameters, if you want. There is a phase and a radial parameter, how many vibrations you have in the radial direction and in the phase direction. Let's see if we can augment the phase direction so that let me see. You see here that you have 4 values for the phase. Here you would have 3 values of the phase. Okay, and I mean, we can compute these functions. They are not simple. I mean, the scale, if you want, of this disk is not simple at all. They are given by zeros of Bessel functions. And what do they look like? Now they no longer look like a straight line. Okay, they look a bit like that. They plot like this. They look like this as a spectrum. And we can listen to them a little. Now it should make a noise. Okay. Okay, and now. So you see what happens. I mean, when you gradually augment the phase or the radial parameters, the sound will become, of course, more and more acute. And now what happens, let me go back to the other thing. What happens is the following. What happens is that when you look at the frequencies for the eigenfrequencies of the disk, when you look at them, the first ones you don't see any shape, okay? But when you keep looking, when you look at higher and higher frequencies, you begin to see some shape which is coming, and when you look at very high frequencies, you see a parabola, okay? And now what does this tell you? This tells you that you can tell, if you want, the dimension of the shapes that you are looking at by the growth of these eigenvalues. So you see, when we are talking about the string, the interval, okay, it was a straight line. Here we look at a two-dimensional object, and you can tell that it's a two-dimensional object because of this parabola. Okay.
So independent of the fact that it is a circle or any.
Okay. Now I will show you what happens for the square. Okay. So if you take the square, okay, which is just the product of two things, then the spectrum is very easy to compute. Okay, I mean, here I'm talking about the spectrum, of course, of the square root of the Laplacian, but I will come to the Dirac operator, which is almost the same thing. Okay, so you get something which is quite simple to compute. When you compute the eigenfrequencies of the square, you see a shape like this. You see it's slightly different from the previous. It's less regular than in the case of the disk. But when you look at it from high frequencies, it looks exactly the same. Okay, so it's very, very similar. Very, very similar. And so now we come back to that. Okay, so we have the square. As I said, this is very simple. So I mean, there is no surprise. It's quite simple. But now I will introduce two other shapes which are very closely related to the square, and which are the rectangle and the triangle. And I will explain you very briefly why I introduce these shapes. So I mean, the rectangle is not difficult to understand either. But you can see that the rectangle here, I took a rectangle which is a union of two equal squares. But you can see that the frequencies, vibration frequencies, are a little bit more complicated than just looking at the individual squares. There are other frequencies, okay? And then you have what happens for the triangle, okay? So you have the triangle, which is also alpha square, not double square, okay? And you can look. Okay, you see, so it's quite easy again to compute the frequencies for this type of isosceles triangle. And I mean, the reason why I show these things is that if you want, after the paper of Milnor, the paper of Milnor is a little jewel because it's one of the few mathematical papers which has one page. So it's a paper which has one page, and it can be explained in a few words. I mean, it's known from the theory of theta functions that there are some, there is not enough room among theta functions. This is because of modular forms. So what happens is that you have two different lattices in a space of rather high dimension, which have exactly the same theta function. And having the same theta function tells you that they are isospectral, even though they are geometrically different. But then gradually, the dimension of these examples, which in Milnor's case were 16-dimensional, was gradually reduced until it was reduced to dimension 2. So what these people have shown, these mathematicians have shown, is that here you have two shapes. Of course, these two shapes have to have the same area if they are isospectral, because the area is the slope of the parabola. If you want, the parabola tells you the area of the shape by the theorem of Hermann-Weyl. I mean, these two shapes are sort of they are isospectral, but they are not the same, obviously. They are not the same geometrical shapes. And if you look a little more, you'll find, okay, other examples. But I mean, the example I am interested in, just to show you the principle which is behind my talk, these two shapes, so I consider the blue shape, even though it's not connected, but don't worry about that. I mean, it's not really important. It's just to simplify the discussion. So the shape, the blue shape and the green shape have the same spectrum. This is elementary to check. I mean, both of them, if you want, are given by isosceles triangles, and one is given by square, the other one is given by rectangle. It's an exercise to show that they have the same spectrum. Sorry. Yeah, it's an exercise to show that they have the same spectrum. Yes, because I'm not in the right one. Just a second. Yeah, so, I mean, this is not difficult to show that they have the same spectrum. So the triangle, as I said, is alpha the square, and you have this spectrum here. Here is a rectangle, which is two squares. Here you have these two shapes, which have the same spectrum. Here is another example, which has the same spectrum. But I prefer to tell you about this shape 1 here and this shape 2. You see, they are not the same, obviously, because in one of them you have a square, in the second you have a rectangle, and in both cases you have triangles, but they don't have the same size. Okay. Now, so it's not too difficult. You can look at the spectrum. In both cases they are the same, exactly the same. They have the same multiplicity and so on, and there are the numbers which are given here when you take the square root of these numbers. Okay. But now what happens is that they have the same spectrum, all right, but they don't have the same chords. What do I mean by that? You see, when you look at these spectra, you will find that there are three, in the scale, in the corresponding scale, there are three types of nodes. There are three kinds of nodes, which are different. There are nodes of the first kind here, the red ones, which are of a certain form in terms of integers. There are nodes which are of the second kind, which are blue, and there are nodes which are of the third kind, which are black. Okay, and what happens is the following. What do I mean by possible chords? You see, what do I mean? Okay, I mean now that you have eigenfunctions. So these eigenfunctions are coming from the drawings that I was doing with the disk or with the square and so on, okay? And now you can take a point, You can take a point. This is how we shall locate the points. Now, if you look at a point, and if you look at the eigenfunctions, you can look at the value of the eigenfunction at this point. Okay? And I will say that the point makes a chord between two nodes when the value of the eigenfunction at that point, the two eigenfunctions, will be non-zero, let's say, okay, to simplify. Okay? Now, what I am saying is, if you look carefully at the two shapes that I had there is one of the two shapes, the one which had the rectangle, in which it's impossible to make a chord which are between the blue and red. Why? Because the corresponding eigenfunctions only live in one of the two pieces. So if there is one in one of the pieces, it's zero in the other piece, and if it's non-zero in the other piece, it will be zero there. So this chord will not be possible. Okay? Now, if you understand this example, you understand the finer invariant, which is behind the scene, and which is allowing you to recover the geometry from the spectrum. And when you look further, okay, we shall see that very soon. But when you look further, if you want, anticipating a little bit, what we shall see is that this is how the notion of point will emerge. In other words, how a point will emerge, if you want, is by a correlation between different frequencies. Namely, a point in the space will actually give you the correlation between the different frequencies. That's how we shall think about a point. Okay? So the space will be given by the spectrum, it will be given by the scale, and the music of the space will actually be done by the various chords which are possible. So it's not enough to give the scale, you also have to give which chords are possible, essentially. Okay? This is, if you want, a simplifying way of putting it, but I will come back to that. Now, when I prepared this talk, this was which I gave already about a year ago in a much simplified form, I was very puzzled by the following thing, because the first thing that I tried to do was to play some music, and at first I tried to play some music with the interval. Okay? Now, can somebody tell me which is the music there? It's very, very easy, you know. See? Pa, 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 pa. Okay? And and you will check, actually, you know, that the only thing which matters when you have these sequences which are written there are the ratios. Because, you see, the ear is done in such a way that it's only sensitive to the ratios. It's not at all sensitive to the additivity, to the linearity. It's sensitive in the logarithmic scale. All right? So, and you can see that these numbers are quite complicated, actually. And if you try to play Au clair de la lune in this scale, which is 1, 2, 3, 4, you will find out that you have to start from something like 110 or something like that. It's awful. It's awful. Okay? And now you think a little more, and you read, of course, you know, Euler and all that. And what do you know? You know that music, actually, you know, the music we are used to, which is extremely rudimentary, is done of two things. It's done of passing to the octave, which is multiplication by 2 of the frequency, and the transposition. And transposition, normally the simplest way would be multiplication by 3, but because you want to come back to have something, you know, which is not too far, you actually take 3/2. All right? And it's a fact, it's a mathematical fact, that 2 to the power 19 is almost 3 to the power 12. Okay, this is a mathematical fact, that when you take 2 to the power 19, and so yeah, so when you take that, it's almost, in fact, I mean, to show you the figure, I mean, when you take the value of 2 to the power 1 over 12, you get 1.059, okay, and when you take 3 to the power 1 over 19, you get 1.059. All right, and of course this is the basis of the well-tempered clavier, you know, and the fact that when you transpose 12 times, you fall back on your feet, and so on and so forth. All right, and what does it mean? What does it mean? Well, it means that if we want to do beautiful music, it's very simple what we should take as a spectrum. What should be the scale in order to perform beautiful music? Well, it's very simple. We should just take powers of q, so q to the power n, if you want, in very simplified form, where q is this 2 to the power 1 over 12, which is almost 3 to the power 2 to the power, 12, 3 to the power 1 over 19. Okay? So you see what we are after. See what we are after? We want to have a nice musical instrument, should be a shape, okay? And that shape should be such that its spectrum look like that, where q is this number, okay? Now we can try. Well, first of all, we can draw the spectrum as I was drawing before. Okay, so what do you get when you draw the spectrum? You get something which doesn't look at all like a parabola. You see, this doesn't look at all like a parabola. Doesn't look at all like a straight line. It goes completely the other way. It goes up exponentially fast. What does this tell us about the dimension of this space? What is the dimension of this space? It's not 2, because it's not a parabola. It's not a parabola going like this. It's not a straight line. It's much, much, much smaller. So it's 0. 0 plus, okay? So when you look at the dimension of this space, the dimension of this space is really 0. I mean, it's very, very, it's smaller than any epsilon positive. Okay, so now we can hunt for this space. And of course, the first natural thing that you would try to get this space would be a sphere. Okay? So if you take the sphere, well, you can compute the spectrum of the sphere, you can compute the eigenfrequencies of the sphere, and you can see that the eigenfrequencies of the sphere, of course, it's an object of dimension 2. So this will never work. This will never work. So somehow, you think you are in bad shape because all the shapes we know have either a straight line or parabolic or even worse. But this is ignoring the non-commutative world. And this is ignoring quantum groups. And what I want to show you is that there is a beautiful answer to that, which is a quantum sphere. So I know that there were talks about quantum groups and so on. So everybody here should know what is a quantum sphere. And as I said, it's dimension 0. And there is a mathematical object, which is called the quantum sphere, which is obtained exactly in the same way as the ordinary sphere is symmetric with respect to the ordinary rotation group. It's exactly symmetric and in the same way with respect to the quantum group SU2Q, okay, which is a quantum group, but which has this object. And when you look at the spectrum of this guy, okay, it has the right behavior. Of course, there is a very tiny term, which is a power of Q, which decays in the other way, but you don't care. You absolutely don't care. But now what I want to show you is how can we test this idea? Well, we can test this idea. Well, we can test this idea because now we have the keyboard coming from this object. So now I made a keyboard, okay, from the quantum sphere. And first I am a little bit tired, so I might make some wrong note, but I will try, okay? Ooh, the sound doesn't work. Ah, okay, so the sound works, okay. Oh God, it seems to have some delay, I don't know. So let's hope there won't be some delay, because it would be a catastrophe. Ça marche? Okay. No, because I was starting au clair de la lune, which is not right. I want to do something more difficult. Now, can anybody in the room give me a number? Don't applaud yet. Can anybody in the room give me a number in the second row? Not 15, because I did it. 17, okay. So you see my point. My point is the following. My point is that this would be a great musical instrument. This would be a musical instrument that would never get out of tune. Okay? The problem then is the following. What type of a geometric space is that? What type of a geometric space is that? And in order to understand what type of geometric space it is, we have to make a big leap in our concepts of geometry. And we have to understand that geometry, one way to understand geometry is quite different from the usual way. It's purely spectral. And it is Hilbert space theoretical. And for that reason, it is extremely congenial to quantum mechanics and to the previous talk. Okay? And what I want to explain is the works that I did with my collaborator Shamseddin, based on this idea. If you want, it's all based on this idea. And well, I should say, but I don't want to spend time on that, what happens is that the invariant I was talking about, which is complementary to the spectral invariant, had already an antecedent in physics, the standard model. There is something which is called the CKM matrix, and that's why I called it the CKM invariant. So first of all, how do we get back to points in a geometric space? Well, we get back to points as giving, when you have a geometric space, you take the Dirac operator, you take the eigenfunctions for the Dirac operator, okay? And then when you have a point in the space, what you look at is a matrix of rank 4, if the space is dimension 4, which is the matrix of inner products of these eigenfunctions at the point. This matrix has small rank because the space of spinors at the point is a space of dimension 4. So it has small rank. It's a matrix of complex numbers. It's a nice self-adjoint matrix and so on. And what I am proposing is that this is the way we should think about the point. Namely, a point should be thought of as a correlation between frequencies. Now, what happens is that at first it looks very weird, this point of view on geometry, but when you think a little bit about it, you will find out that the information we have about the space in which we are is essentially of that nature. Because we are unable to go to the other galaxies and so on. The only thing that we get is spectral information coming from very far out in the universe. Moreover, this information, for instance, is redshifted and so on, which gives us information about the time these cells we get this information from figures. And the only reason why we believe that there are real things out there, like the galaxy, the Milky Way, is that when we take the picture of the galaxy, X-ray, for instance, or infrared, or we get the same picture. So what I'm saying is that it's not on the spectrum, but it's a correlation between the different eigenvalues. The fact that we can create and there are correlations essentially. So what we did with my collaborator Shamsuddin was to attack the problem of understanding which space-time we are, okay, from this standpoint. And the way we attacked it was the following. There are, if you want, two informations which come. Oh, there is some ghost. You will see that. Ça marche? So you will see other ghosts very soon, okay? Okay, so what happens is the following. What happens is that we have two informations about space-time, and one comes from general relativity, which is best encapsulated by the formula, g mu dx mu dx nu, but more precisely by the Einstein action, which is the integral of the scalar curvature, okay? But then there is another piece, okay? I mean, if it was just gravity, everything would have collapsed since long, There would be nothing going. There is another term, which, for the action, which covers everything. So there is this other piece here, and I have been told by my collaborators that it's always a mistake to show the formula for this other piece. But still, I cannot resist to show you this formula because some people might believe that it's very simple. You see? So there is this other piece here. And this other piece, of course, many people would picture it by showing you the elementary particles and so on. But in fact, mathematically speaking, it is this. And even when I have written this, I have not shown you the full picture. Why? Because in the full picture, this guy is actually minimally coupled to gravity. So I mean, the formula which I show you here is in flat space, okay? And it has 3 pages, and it takes about 4 hours to typeset it, and so on. So and when you were talking about chemistry and everything, it's all contained there. Everything is contained there. Of course, I mean, you have to make a lot of computations and so on, but that's the core, okay? And of course, there is a basic task. There is a basic task that scientists have, which is to understand what is behind that. I mean, you cannot, okay, you can say, fine, we have introduced the W because we wanted because the weak interaction is weak, so we wanted to have a heavy boson and so on. Fine, this is what the physicists would tell you. But for a mathematician or for a scientist, this is not a satisfactory explanation because you want to understand what this is. Okay. All right. So to tell you the story very briefly. I mean, I don't want to go into much details, but I want to say the following. I want to give you a very, very simple reason why this extension of geometry, which is sort of begged for by the musical shape, for instance, is essential in this story. The reason why it is essential can be explained mathematically very, very simply. You see, when you look at the Einstein part of the Lagrangian, this Einstein part has a beautiful group of invariants, which is called a gauge group, and which is a group of diffeomorphisms. So that part has a very geometric meaning because it has a group of invariants which is a group of diffeomorphisms. And this group of diffeomorphisms is the reason why we had to specify where we are in an invariant manner. Okay? It's the essential reason why. This group of invariants is the reason why we had to think about it. Otherwise we could have given coordinates. It doesn't work because we have this invariance group by diffeomorphisms. Now, it's not the only group of invariants of the story because there is another group which is called the group of gauge transformations. And this group of gauge transformation is quite a priori different from the group of diffeomorphisms because it's like the group of maps from the manifold to a small group. Let us say SUN to simplify. Okay? So what does it mean? It means that the full group of invariants of the story is neither the group of diffeomorphisms nor the group of maps from the manifold to SUN, but it's a semi-direct product of the two. Because the diffeomorphisms shuffle the gauge transformations. Okay? They act on the gauge transformations. So, you see, now there is an obvious question. Can you find a space X? All right, we always think of space-time as X, okay? So that when you look at the group of diffeomorphisms of X, okay, I mean, it will be equal to this group that I explained, namely this semi-direct product of ordinary diffeomorphisms by gauge transformations. Okay, I mean, it's only when you find such a space X that you can claim that you have geometrically understood what is going on. All right, okay. Now, the very extremely simple fact which I ask you to reflect about is the following, is that, of course, diffeomorphisms can be translated algebraically, and if you take the algebra of let's say, smooth functions on a manifold M, then the diffeomorphisms are nothing else but the group of automorphisms of this algebra. Okay? There is nothing else. But what I ask you to think about, this is an extremely simple fact, is that if you replace C-infinity functions on M by C-infinity function tensored by matrices, Mn of C, which is the same thing as C-infinity maps from M to Mn of C with the product of matrices and so on. Well, then the group of automorphisms of this new algebra is nothing else but the semi-direct product of the group of maps from the manifold to SUN by the group of diffeomorphisms. So you see that by an extremely minor extension of geometry to admit matrices over the algebra of functions, which is something very ordinary in case theory and all that, then you gain the fact that you have a geometric interpretation for the group of invariants of the Lagrangian. Right away. Okay? So what we did with my collaborator, Alain Sedin, we wanted to develop geometry in such a way that geometry would no longer be dependent upon coordinates or anything like that, and it would be spectral. So how to develop geometry in a spectral manner? The first step is to understand that in the Riemannian paradigm for the distance between 2 points in a geometric space, which, as you know, is the infimum of the geodesic, infimum of a distance, a path from one to another, there is something which is very unpleasant in this formula. The thing which is very unpleasant in this formula is the square root. If you know a little bit about computers, and if you have used a computer, you know that the computer doesn't like square root at all. Okay, if you put a square root, especially for a space with metric, it will not like it at all. So there is a solution to this problem of the square root, beautiful solution, which was found by Paul Dirac. So what Paul Dirac found, he didn't find the square root for g mu dx mu dx nu, he found the square root for the Laplacian. And in fact, if you look historically, it's not really Dirac who found it first, it's Hamilton. Because Hamilton in his work has written d by dx times I plus d by dy times j plus d by dz times k, where I, j, k are the quaternions, and of course, this is the Dirac operator. And he checked, of course, that the square of this operator is Laplacian. Okay, so what happens now, what is the idea? The idea is very, very, very simple. The idea is to replace a geometric space, which in Riemann's case is given by coordinates and the g mu dx nu, to replace it by the algebra, of course, and the line element. But the line element should be thought of as the physicists view it, namely, for physicists, this thing has a meaning. They call this a propagator for the Dirac operator. Okay, so it's the inverse of the Dirac operator. And when you develop this thing, what you will find out is that you don't lose anything. Namely, you can recover the distance between 2 points in a different manner from Riemann, not by putting a tight rope between the 2 points, but by sending a wave from point A to point B with a constraint on the vibration of that wave. That wave cannot vibrate faster than 1, because what I ask is that the commutator of that function with the Dirac operator is less than 1. That forces the Lipschitz norm of the function to be less than 1. And when you compute this maximum, you will find exactly the geodesic distance. But now it has a big advantage, which is that it no longer requires that the space is path connected. It works for discrete spaces. It no longer requires that the space is commutative, because it also works for when the algebra is non-commutative. And when you talk about quantum states, quantum mechanical states. And moreover, if you think a little more, you find out that the physicists had done it before. How did they do it before? Okay, that's a funny story, so I can't resist telling you. How did they do it before? You see, if you look at the previous picture, if you look at the previous, that one, well, there were 2 French guys who actually did it. Not from Seattle to London, but from Dunkirk to Barcelona, during the Spanish War. And they were almost killed several times because they were taken as spies. Of course, they had telescopes on tops of hills. They were measuring angles and so on. Okay, and so they came back, and then they said, this is 1/40 million parts of the circumference of the Earth. Okay, and then somebody took a metal bar, okay, completed exactly that length. It was a platinum bar. Perfect. That was the unit of length. Extremely practical. Imagine you are in another solar system and you want to measure your bed. Okay, you have to come to Paris, compare to this. Okay, fine. Thank you. Okay, perfect unit of length. Okay, but then there was much worse. So there was this unit of length, and we all were learning at school. The unit of length has been deposited in Pavillon de Breteuil near Paris, and so on. No. Okay, except that in 1927, I think, there was a meeting of the exactly the units. Bureau International des Poids et Mesures, and somebody said, oh guys, your unit of length is changing length. And then they told him, how can you tell? We are amazed. How can you tell? It's a question of definition. And he said, look, I measured it with a krypton. I compared it with a krypton wavelengths. I counted how many krypton wavelengths there was, and it was changing. This is bad for unit of length, definitely. Okay, so it took time, but eventually the physicists realized that there was a much better unit of length, and that unit of length was a wavelength of a certain kind, of a certain spectral ray, and so on, of a certain chemical. Okay, at first it was krypton. It was the orange line of krypton. Then cesium. Moreover, they talk about time instead of length, but that doesn't matter. It's just a trivial change of variables. Okay, well, okay, by the speed of light. And probably, gradually, of course, it will come to hydrogen. Why? Because imagine you want to unify the metric system in the galaxy. Okay? You have to have something, or in the universe, you have to have something which is present everywhere in the universe. So you have to take the simplest chemical, and not cesium, not gold. You know, gold is very rare. Okay? So what you have to do is to take the most common chemical and give this as definition. Now, if you think a bit, that's exactly the definitions that we have with the Dirac operator and with the spectrum of the Dirac operator. Okay? So what I am proposing is a new idea of a geometric space in which, if you want, the algebra of coordinates, okay, which is A, which is something very vague, as I said, because this algebra can be just a fundamental algebra, and it depends very little on the actual structure. And the line element is extremely important. And what is really important is that these two things actually interact, that they are acting in the same Hilbert space. That's really where the interaction of the two things is really taking place. Taken individually, they are not much flesh. The algebra itself, because I take measurable functions, is not much. The operator is just spectrum, of course. This is the only invariant. But when you let them interact in the same Hilbert space, then everything happens. Okay, so what did we find? First of all, we found that there was a way to reconstruct a manifold from this data. I mean, this is not difficult, but what was much, much more difficult was to characterize which are the triples which come from manifold. Okay, so this is a technical mathematical theorem. But then what we found is that there is, in fact, if you want, the following model that emerges now for the space-time, namely that instead of just being the naive idea that, let's talk about space, okay? That space is simply a manifold. Then what emerges from this is that you have more freedom. And what you find out is that because exactly of the gauge group and because of these matrices and so on, in fact, the natural structure that emerges is that you have a manifold times a finite space. Okay, and this finite space, you should never think about this finite space as being a commutative space, because, for instance, here I had matrices, so matrices are given by non-commutative space, okay? And then you can ask me, but what is the geometry of this finite space? Because to have a geometry, you need to have a Hilbert space and the Dirac operator. And you find out that the physicists have this Dirac operator. This is what they call the Yukawa coupling matrix for the particles. And the Hilbert space for the finite space is finite dimensional. Okay? Now, what we did for several years with my collaborator Shamseddin, we took this finite space from experiment. And it's only recently, about a few years ago, that we could actually classify the finite space and understand why it is the space it is. This comes from a classification, which I won't enter into because it's related to mathematics, and it's related to the fact that there is behind the scene, when I talk about the Dirac operator, okay, there is a square root, and this square root, exactly when you take a square root, there is an ambiguity, and the ambiguity which is there is coming from the spin structure. And so there is a mathematical theory which is ruling all this story behind the scene, and which is telling you that, if you want, it's not just Hilbert space stuff, functional analysis. No, there is a lot of topology. And this topology is actually what is called KO theory. So it turns out that for reasons which can be explained, the finite space which is there is essentially the simplest finite space which has dimension 0 as far as the spectrum is concerned, because it's finite, but whose KO dimension is equal to 6. So when you classify these spaces and so on, you find that essentially the simplest one, this is what we found with Ali Shamseddin, correspond to an algebra which is 2 by 2 matrices over quaternions plus 4 by 4 matrices. And when you compute with this, now you have to ask, fine, you have found this space and so on and so forth, but how do you compute? How do you make now a link? Because you have to do that. How do you make a link with this enormous formula coupled with Einstein gravity? Because it's not enough to have the standard model. You need to have the standard model minimally coupled to gravity, otherwise you are nowhere. And the claim is the following. The claim is that we have an explanation which is simple. What do I mean by simple? This is what we have to discuss. You see? What do I mean by simple? Let me make a definition of simple. For me, something is simple if it can be explained to the Neanderthal man. Or perhaps Cro-Magnon man, okay? Now imagine that you have to explain to the Cro-Magnon man what is the integral of the scalar curvature. That's tough, That's really tough, okay? Okay? But I claim that the formula that we have is much, much simpler. Because what is the formula? How do we get this formula? We get this formula by counting the number of eigenvalues of the line element which are bigger than the Planck length. So it's just counting. We just count the number. We get an integer, okay? Now, using very fancy tool, of course, we expand this integer. We expand this asymptotically. What do we get? We get the Einstein action, first term. Then we get the Higgs particle which appears, we get all this stuff and so on. Now, I will finish by telling you the story. There were 2 episodes which were very stressful, and I'm sure there will be others, and I hope I won't be around when they will happen. So the first episode was the following. When we built up this theory with Shamseddin, that was in '96, our optimism was short-lived because 2 years, because first of all, we had put the finite space to have KO dimension 0, okay? So what happened was that by doing that, it was impossible to have neutrino oscillations. So 2 years later, in '98, neutrino oscillations were discovered, and I remember discussing with Bryce David and telling him you can throw everything to the waste, it's bullshit, okay? Because, we cannot get the neutrino oscillations which have been observed. So then a long time passed, and I remember actually seeing my teacher, Jacques Dixmier, and each time I would see him, he would tell me, you are wrong to abandon so easily. You are totally wrong. And it's only in 2006 that, because I was writing a book with Mathilde Marcolli, that actually, I was obliged to come back to that. And in fact, what she did was to put down this formula and tell me, prove that what you are doing with Ali gives this formula. Okay, so I did it very painfully and all that. And at some point I realized I'd been completely stupid of assuming that the KO dimension of the space, of the finite space, was 0. Why? Because in the meantime, people had found these quantum spheres. And when you have the quantum spheres, I showed you that it has dimension 0 metrically, but the KO dimension, of course, is 2, because it doesn't change from the ordinary sphere. It's a rigid thing. So then there is a dissociation between the KO dimension and the metric dimension. So why not then try the different KO dimensions? And when I tried KO dimension 6, not only it gave the neutrino mixing, and Majorana mass is for the neutrinos and so on, but it gave the seesaw mechanism, which is a very subtle mechanism, which, even if you have Yukawa couplings which are the same magnitude as for the quarks, gives you extremely small masses for the neutrinos because there is a cancellation and there is something which comes in the denominator. So this came in from the calculation. I didn't know the seesaw mechanism came in, okay? But then, again, so that was in 2006, okay? That was in 2006. Again, for 2 years, we were happy, giving talks and so on. And then in 2008 came the first news from the Tevatron, which was excluding the Higgs mass at 170. And at that time, in our work with Ali Shamseddin, we had shown, indeed, as for the ordinary standard model, that if you have the model at unification and so on, it's impossible to make the mass lower than 160 or 170. It has to be like that, otherwise the model is unstable at unification. Okay? So we were sort of stuck. And, I put immediately something in the blog, and so on and so forth. Okay, and so the 4 years passed, and each time I was giving this talk, for instance, I would end on a very sad note, which is that, this theory is making predictions. It makes many predictions, actually. It was predicting the top quark mass, and that is fine. I mean, that gives the correct value. But then we get the Higgs mass wrong. And so a kind of miracle happened around April, May, and so on, which is that totally independently of our work with Shamseddin, physicists began to worry, physicists who are, model builders and so on, they began to worry that the standard model wouldn't be stable until unification, and they tried to find some ways of curing that disease of the standard model. Okay, what did they find? They found that if you would add a scalar field, which would have a quartic self-interaction, which would couple with the Higgs in a certain manner, which would couple with other particles in a certain manner, and so on, then the standard model would be robust until unification, and you could still save the Higgs mass to be small, 125. Okay. Now, believe me or not, but then we looked at our 2000 paper, 2006 paper, and that field was there. And we had ignored it. We had ignored it because we had said this field will have no influence whatsoever. What did we say? We said, okay, this field is there, but I mean, what can it do? So we fixed it to its vacuum. It's a field which is giving Majorana masses to the neutrinos, okay? Okay. So we said, okay, we set this field to its vacuum, and then we ignore it, and so on. All right. Now, when we look back, fortunately the paper was already published. I mean, it's not something we are adding by hand. Nothing like that. Absolutely nothing like that. The paper is published, the paper is there, okay. And it turns out that all the couplings are the correct sign, the correct value, to have the correct coupling with this, and so on. So what does it mean? It means two things. First of all, it means that the standard model survives up to unification with this field, okay, with this low value of the Higgs mass, okay. And moreover, it means that, some people actually had written in several of these papers that it could be an explanation for the dark matter. So it's a very simple model, it's a very simple model. It's not a model because of neutrinos and so on. So, it's a very simple model. It's not a model. It's a model which is extremely conservative. We have been incredibly conservative because our model doesn't predict any proton decay in a new particle except for that one. But it's a particle which will have a mass of the order of 10 to the 11 GeV. So it's very, very high. It's a boson. It's a boson. But so now, if you want, we are in a more up situation. Might be it will last 2 years or I don't know what. But what I find extremely satisfactory, if you want, is that this theory is at the same time extremely simple in its principle, because the principle of the theory is to tell you that there is a fine structure in space-time. Space-time is not just a manifold. There is a fine texture, exactly as there is a fine structure in spectra. Okay? And what we are doing when we are doing experiments in CERN and so on, we are in fact looking with a huge microscope, and we are uncovering this fine structure. And so the fact, if you want, is that in order to understand this fine structure, you have to dilate a little bit your ideas about geometry, and you have to rethink about geometry, And for that, you know, there is a lot of payoff because, of course, that geometry is perfectly adapted to quantum mechanics. I mean, it's like saying geometry is born, you know, in quantum mechanics because it's born from Hilbert space and the line element and everything. Moreover, you know, it only uses observable quantities because it uses invariant quantities on the space. So the hope is, if you want, that somehow, I mean, the development, and in particular, you know, with this, for instance, the fact that you had talks about quantum groups and all that, I mean, that the development of this geometry is only at a very, 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 very initial phase, only at the very beginning, and that the process that we have to do, the mental process that we have to do is extremely hard. It's a little bit like what you were saying about quantum mechanics, that you no longer should have a naive geometric picture. Same here. What I am saying is that our brain is an incredible utensil which perceives things in momentum space, or the photons that we receive, and manufactures a mental picture, which is geometric. But what I am telling you is that I believe from all of what I said, that the fundamental thing is spectral. And that the fundamental thing is of that nature. And that somehow, in order to think, we have to do this enormous Fourier transform. You see? It's a Fourier transform, really. It's a Fourier transform. And it's a Fourier transform not from functions, but it's a Fourier transform on geometry. So what I have described to you by talking about the music of shapes is really the Fourier transform of a shape and the fact that we have to do it in the reverse. And this is a function that the brain does amazingly well, you know, because we think geometrically. So I think
Thank you, Alain, for this unbelievable lecture. I mean, yes. I knew about the Podler sphere, but I had never listened to it. That's quite amazing. So, are there actually other quantum groups that, other than SUQ2, for example?
I don't know, but I mean, you know, the two-sphere, of course, is the most tempting, and it's very symmetrical and so on. I don't think it will be easy to beat, you know, really. I mean, the two-sphere is really pretty good, I think. But of course, one should try others. I mean, yeah, of course.
Alain, I have a question which I hope is not totally out of your perspective. What I heard suggests me that one thing which always fascinates me is the equation of spectra.
Yeah.
You are a 19th century physicist, and you look at the spectrum of hydrogen, you have a bad resolution, you have just lines, and you have the Balmer formula, fine. Then you have a better spectroscope, and you begin to have the fine structure. And it turns out that the centroid of this fine structure still obeys the Balmer formula. And then you go to a finer scale, you have the hyperfine structure, and again, it turns out that the centroid of the refined spectrum...
Can I answer?
Yeah, and do you have a mathematical tool for showing this kind of invariance?
No, but let me answer, because this is exactly the place. By the way, there is this amazing book by Heisenberg, and it's related to this, okay? So let me answer the question. You see, physicists have a nose to find formulas which are robust. Yes. What do I mean by this? I don't mean the Balmer formula. I mean the Ritz-Rydberg formula.
No, okay. Yes, sure.
You agree with me?
Yeah.
Okay. So what does the Ritz-Rydberg formula tell you? The Ritz-Rydberg formula tells you that spectral lines are in fact best indexed by two indices, alpha, beta. Alpha and beta could be anything, colors, whatever you want, whatever you like, okay? And the Ritz-Rydberg principle tells you that you have a combination law, which is called the Ritz-Rydberg combination law, which is that nu alpha beta plus nu beta gamma is equal to nu alpha gamma. So some frequencies add. Okay? So there is a partial structure, which is that some frequencies add. Now, Heisenberg had, at some point, the hay fever. He had it so badly that his university told him, go to an island which is known not to have any tree, which is not far from the coast. He went there for 2 weeks. There was only one house, I think, on the island, and an old lady who took care of him. He had, inflated. Okay, so he had an extremely bad allergy. And Heisenberg made the following reasoning. He said, if we were in the classical world, we wouldn't have the Ritz-Rydberg principle. We would have a group. Namely, all frequencies would actually add. Namely, we would have a group of frequencies, and by Fourier transform, we would come back from this group to the space, which would be a torus, and to the Hamiltonian evolution in this space, which would be given by the energy. And Heisenberg said, let's do the same thing. If we had a group of frequencies, then we would take functions of these frequencies as being our observables, and when we make the product of two functions, because we are in Fourier, we would have the convolution product, namely f1 star f2 of nu would be the sum of f1 of nu1 times f2 of nu2, where nu1 plus nu2 is equal to nu. This he knew very well. Nu, okay? Okay, he knew this very well. So what did he say? The Ritz-Rydberg principle tells us this is not the case. What we have is this law, not that one. But let's do the same thing. Let us say that f1 star f2 of nu alpha beta will be equal to the sum of f1 of nu, alpha gamma, let me say, nu alpha beta F2 of nu beta gamma. Okay? And Heisenberg rediscovered the matrices. This is a matrix product. This is a product of two matrices. And when he was alone in this island, he found out that matrices don't commute. He was very scared. And he made computations by doing the conjugation by exponential of IT times the energy. And he found this was giving him exactly the right evolution equations. And he was so happy when he found out at 3 o'clock in the morning that he climbed on top of a rock, which was quite a hard climb. And he waited until the sunset, until the sunrise on top of this rock. Okay? But you can see that that point, very precise point in the history of physics, is a point when it was discovered that the quantum observables do not commute. It is exactly at that point that it was discovered that the quantum observables do not commute. And so if you want, it was discovered that the phase space of a microscopic system, a very small system, is actually a non-commutative space. And that's what's behind the scene all the time. So what you said is the following, is that, the way I understand it is that some physical laws are so robust that if they are understood correctly, they tell us that there is a marvelous mathematical structure which is underneath the law, not the values of the numbers or anything like that, but there is a mathematical structure which embodies it. And I think, in a way, one important role of scientists in general is to try to unveil these laws. Okay, well, of course, with many trials and errors, nobody is right. We are experimentalists also in what we are doing, in the sense that we are trying something and it might be wrong, it might be partially right and all that. But somehow, it's extremely important indeed that a physicist would tell us, well, I think this law, this principle, is valid. And then a mathematician can take this principle, not make a mathematical, try to understand what does it mean, how it can affect. And I think if you want, the way that you are saying that the quantum world affects your thinking about reality, there is a similar way about geometry and mathematics. Namely, the irruption of the quantum in the mathematical scenery is not really totally absorbed. It's wrong to say that it's totally absorbed, because mathematicians still like to think about, commutative space, Sheaf schemes, and all that. I mean, they are very tightly stuck by this. I mean, they are, commutative algebra is so much easier. Oh, by the way, let me tell you a wonderful, I finish on that. I met Etienne Klein this summer, and he's a great specialist of anagram. Now, I suppose you know what anagram is, yes? For instance, I once received an email from a friend, and this email was like this. I thought my friend was nuts. He said, je suis alençonnais et non alsacien. Si tu as besoin d'un conseil nana, rendez-vous au coin anal. So I said, my friend is nuts, It happens sometimes, We are doing so much hard work that,
Is he a mathematician?
Mathematician,
so
yes.
we can believe.
Yeah, and then I began to think, because the guy is clever, I began to think, je suis alençonnais et non alsacien, rendez-vous au coin anal. And I found Alain 4 times. Okay, so he had written my name, an anagram for my name 4 times. But I want to end with this anagram of Etienne Klein, which is wonderful. So I don't know if you will be able to make it, but let me tell you the difficult part. So the difficult part is l'horloge. L'horloge ici-bas. You know what I mean? You have seen this type of clock where you have 2 angels which support, a kind of a clock, something like that. Okay, l'horloge des anges ici-bas. And you know of what it is the anagram? Le boson scalaire de Higgs.
There's no nicer way to finish a conference.